All right, I'm testing the transcription now to make sure that it's working. Looks like that's working. We'll go ahead and close that. And then let's get started. Let's go to, please start up your terminal and go to the place where you store your local copy of the Git repository. So for me, that would be KCGI, intro speech understanding, and then do a git fetch release. So if you notice that when I list this directory, it only lists up through lecture 4, which is last week. But if I git fetch the release and then merge the release main with this repository, let's give it a comment. Let's not give a comment and see what happens. Let's say allow unrelated histories. Well, I'll go ahead and add a comment. And that will merge it. And now if we do a list the directory, we see that it includes lecture 5. So if we change into lecture 5, we can start Anaconda. So for example, we can start Jupyter Notebook. Notice I'm typing the word Jupyter space notebook. So take a look at the commands here. We have git fetch release. That's how you fetch a copy of the repository. And then git merge release main, allow unrelated histories, -m, and then whatever comment you want to make in your merge. And then change directory to lecture 5, and then type Jupyter Notebook. And that's really all that you need to type this time, because there is a Jupyter Notebook in this directory. So from here on out, we'll be able to work directly in the Jupyter Notebook. So here's lecture5notebook.ipynb. We'll open that. And we discovered that this week's lecture is about NumPy and Matplotlib. We have finished with the overall introduction to Python. Last week, you learned about dictionaries and tuples. The week before that, you learned about lists. And the week before that, you learned about the fundamental Python data types, strings, floating point numbers, and integers. This week, we're going to learn about NumPy, which is the package that's used for plotting, the package that's used for doing numerical computations in MATLAB, and Matplotlib, which is the package that's used for plotting. So we can click on NumPy to learn more about NumPy. And here's powerful n-dimensional arrays, numerical computing tools, open source, interoperable, performant, easy to use. These are the features of NumPy. NumPy 2.3.0 has been released on June 7th. Here's some information about how to try it out. In fact, you can even try it in the window, directly in the browser window. The other thing we're going to learn about this week is Matplotlib, which is used to create plots. Here's an example of a plot. Here are lots more examples of things that you can do in Matplotlib. You can do plots of this kind, or you can do scatter plots, bar plots, stack plots, fill between plots, stem plots. All of these statistical distributions can be done, pie charts and hex bins. You can do plots with gridded data. You can show images, or you can do contour plots, or barb plots, or quiver plots, or stream plots. You can do irregularly gridded data, so you can create a contour plot like this, and on that you can create a contour plot from scatter plot data, where you see that the dots in these plots show where the data are in their XY coordinates, and then the Z coordinate is depicted with a contour line with a height. You can plot three-dimensional. So these are all examples, and if you click on it, you can go to a place where it shows the code to create that example. This week, I'm just going to show really the basics of using NumPy and Matplotlib. And the fundamental feature of NumPy is really that it uses arrays in order to do linear algebra. Linear algebra means matrices. It means matrix multiplications. So first of all, let's import NumPy. And if this has an error, then you need to do pip install NumPy. So if that had an error, then I would do !pip and then install NumPy. If I run this now, it will give me an error and say NumPy already exists, requirement already satisfied. Instead, I want to import NumPy, but actually, more frequently, we don't want to type NumPy every time we want to use one of its functions. And so more frequently, we'll import NumPy as NP. And what that does is it allows me to use the NP dot format
boom.
rather
There we go.
than specifying the function that I'm trying to import using the words NumPy. I can just specify it as NP dot. So in this case, I want to create an array which has the same contents as the list 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5 by itself is a list, but now I can specify that it should be an array. And so, for example, I can print the type of X is, and then let's print the type of X, and you can see what the type is. The type of this 1, 2, 3, 4, 5 is a NumPy ND array. ND array stands for n-dimensional array, and it's n-dimensional meaning that it can be one-dimensional, as shown here, 1, 2, 3, 4, 5, or it can be two-dimensional, as in a matrix, or three-dimensional, as in a block of numbers, or any dimension that you like. So for example, suppose we want to create the array, the vector x equals 0.1, minus 4, 0.25. I can do that by typing x equals numpy array 0.1, minus 4, 0.25. Suppose I want to create the vector y is equal to 3, 0.2, and 5. I can create the array 3, 0.2, 5, and I can feed that list into the np.array in order to get that array. The dot product between two arrays, the dot product between two vectors is the sum from I equals 1 to 3 of x sub I times y sub I. So it's 0.1 times 3, which is 0.3, plus negative 4 times 0.2, which is minus 0.8, plus 0.25 times 5, which is 1.25. And when you add all of those numbers together, you get the dot product, which is 0.75. And we can get that by typing np dot dot. That will calculate the dot product between x and y, which is 0.75. The other linear algebra feature that you can do is the multiplication of matrices times vectors. So if we have the vector x and we want to multiply it times the matrix W, we just need to define the matrix W and then do np.matmul. Here's the np.matmul command. Multiply the vector x times the matrix W. So what this means is basically it means taking the dot product between the vector x and each column of W separately. So we take the sum from I equals 1 to 3 of x sub I times W sub I in the first column. And then the second element of V is the sum from I equals 1 to 3 of x sub I times W sub I in the second column. And the third element is the sum from I equals 1 to 3 of x sub I times W sub I in the third column. So for example, if I make the matrix W to be 1, 1, 1, 0, 0, 0, minus 1, minus 1, then the resulting vector will be minus 3.65, 0, 3.65. I can create the matrix W by creating a NumPy array, which is a list of lists. Notice what we have here. So let me first of all create something called list of lists. And then let's say print the type of the list of lists is, and then let's print its type. Its first element. I'll print some new lines here to give us some space. Let me add a new line at this point as well. And then finally, I can say, what is the type of the first element of the first element? And then let me do one more thing. Rather than rather than just printing the type of the list of lists, let me make it a NumPy array. Let me print the type of this NumPy array. And let's find out what the type of W is after I create a NumPy array from that. What I have is that, first of all, I have this list of lists, minus 1, 0, 1, minus 1, 1, 0, minus 1, 1, 0, minus 1. That's a list. The 0th element of it, 1, 0, minus 1, that's also a list. The 0th element of the 0th element is an integer. It's just the integer 1. But now if I create a NumPy array from it, 1, 0, 1, 1, 0, minus 1, 1, 0, minus 1, that's a NumPy ND array. So by calling np.array, I've converted it into a NumPy n-dimensional array. And the reason I want to do that is so that I can easily multiply a vector times that matrix. So if I type np.matmul, it computes the matrix multiplication between x and w, and it gives me the result, minus 3.65, 0, 3.65. You can see that that's the result of multiplying this vector x times this matrix w. I get the vector minus 3.65, 0, 3.65. The NumPy dot and NumPy matmul are so useful that we can abbreviate them with the at symbol. The at symbol is a dot product if you're multiplying two vectors. So if you have x at y, then that means take the dot product of x and y. If you type x at w, that means take the matrix multiplication of the vector x with the matrix w. So the at symbol means matrix multiplication unless you're multiplying two vectors. So really the main purpose of NumPy is to do these vector arithmetic. So we can do vectors and matrices and multiply matrices together. Sometimes though you don't want to do matrix multiplication, sometimes you just want to take the cosine of every element. So let's say 0, 1, 2, 3, let's say we want to square every element. We want to compute x squared. In that case, we want 0, 1, 4, 9. So we can say the square of x is, and then we'll print x squared. And we can also take the cosine of every element.
I'm not sure I understand.
Sounds like my agent is talking to me. And what's really interesting is we can also take the product of two arrays. Let's take the product of the array x and the array y. And instead of the at sign, I will use the asterisk. The asterisk as a multiplier means do array multiplication, which means multiply every element of each of those two arrays together. Let's remember what x and y are. X is 0.1 minus 4.25, y is 3.25. So their array product is going to be another vector. It'll be the vector 0.3, comma, minus 0.8, comma, 1.25. So rather than adding them all up the way the dot product does, the array multiplication will just create another array of the same size. So let me go ahead and do that. I will take the square of every element, and the cosine of the square of every element gives me 0, 1, 4, 9. The cosine of every element gives me 1, minus 1, 1, minus 1. And I've defined x to be 0, 1, 2, 3. So let's just take the first three elements of it to multiply times y. Okay, so 0, 1, 2, 3 squared is 0, 1, 4, 9. 0, 1, 2, 3, the cosine of pi times that. Let's see, the cosine of pi times that. The cosine of pi times 0, 1, 2, 3 is 1, minus 1, 1, minus 1. And the product of 0, 1, 2 times 3.25 is, let's see, 3 times 0 is 0. 0.2 times 1 is 0.2, and 5 times 2 is 10. So we get an array product output, which is the array x 0 through 3 multiplied by the array y. So that gives us two different ways of working with these long signals. We can either multiply one of these long signals by another one, or we can take their dot product using matrix multiplication. And that's really powerful because that allows us to do computations with many, many numbers all at once. It allows us to do signal processing. It allows us to do machine learning. It allows us to do data science, very generally to do data science. Often you need some special arrays. So I've shown you one of the special arrays, pi. Let's print what pi is. Pi is a special array, but it's actually just a scalar. It's the scalar 3.14159, It's the ratio between the circumference of a circle and its diameter. Other special arrays are the array full of zeros, the array full of ones, the identity matrix, the integer range, and the linear space range. So let me compute these. First of all, NP0 is 3, 3. That's a matrix of a 3 by 3 matrix of zeros. NP1 is 3, 3. That's a 3 by 3 matrix of all ones. NP identity with a size of 3. That's the 3 by 3 identity matrix. And notice that I just gave it one argument. This one argument tells me the size of that resulting identity matrix. The integer range from 2 to 6 are the numbers 2, 3, 4, 5. Right? So this is exactly the same as taking, we could also compute this by taking the array of the list. Let's see. The list will be something like n for n in range from 2 to 6. Right? So this will do a for loop. The for will set n equal to each integer from 2 up through just before 6. And it will create a list with those elements, and that will create the same array. That was never closed. So I need another parenthesis there. There we go. So 2, 3, 4, 5 is the integer range from 2 to just before 6. We could also compute this as NumPy array of n for n in the range 2 to 6, which gives us 2, 3, 4, 5, right? You could also compute that using linear spacing. You could go from 0 to 6. You could go from 0 to 1 with 6 steps, and that would give you 0, 0.2, 0.4, 0.6, 0.8, and 1. Or we could do, let's see, let's print NumPy linspace. Let's say that we wanted to do 2, 3, 4, 5. It looks like we want then to go from 2 to 5. And the number of steps we want is exactly 4 steps. The difference between linspace and range is that linspace includes the ending number, right? Linspace includes this 5, which is the ending number. So it goes 2, 3, 4, 5, whereas a range just doesn't include the ending number. A range set we did from 2 to 6, and it printed out the numbers 2, 3, 4, 5. Right? Let me add a new line after this one. So the A range goes 2, 3, 4, 5. The original Python range also goes 2, 3, 4, 5. But in order to get the same results from linear space, we need to include the ending number. If we want 2, 3, 4, 5, we need to specify that it starts at 2 and it ends at 5, and it includes 4 uniformly spaced numbers in that range. So those are special case matrices that we can use. Now we have all of the variables that we need. Let's see, I wanted linear algebra, array mathematics, and special arrays. And now I need to learn how to plot. I showed you before that Matplotlib has all of these different kinds of plots. I can look at all of these examples, these kinds of plots, scatter plots, bar plots, stem plots, error bars. I'm just going to introduce just a few of them. So let me, it doesn't jump down correctly. Now we've installed Matplotlib, let's import it. Again, why can't I run this? Maybe my kernel has died. I think my kernel has died, so I'm going to actually kill this and kill the kernel and start over again. Let's run Jupyter Notebook again and start over from the beginning. There's Lecture 5 Notebook. Here we go in Matplotlib. So Matplotlib creates figures. So first of all, we'll import matplotlib.pyplot as PLT. Just like with NumPy, we don't want to have to type out matplotlib every single time. And so we import the pyplot sub package as PLT. And then we can create a figure. And the advantage of separately creating a figure is that we can specify the size. So if I want a much smaller figure, let's say I wanted a 2 by 2 figure, I could specify that it's 2 by 2. And that results in a really tiny figure. But I don't really want that. I want a figure that has plenty of space, so I'll say that it's going to be 14 by 4. There's a 14 by 4 figure. With this, I'm going to say from that figure F, I want a 2 by 2 array of subplots. So S will then be a 2 by 2 array of subplots. I have S of 0, 0, S of 0, 1, S of 1, 0, and S of 1, 1. Let's give them each titles. S of 0, 0, set title. This is plot 0, 0. And let me do the same thing with all of the others. I think that set title is the right command. I don't remember actually. Let's find out. S of 0, 1, that will be plot 0, 1. S of 1, 0. And S of 1, 1. I think set title is the right command. Let's find out. There we go. This is plot 0, 0 is just a straight line. Notice that plot 0, 0 is plotting the input. The x-axis is 1, 2, 3, 4, 5, and the y-axis is 1, 1, 1, 1, 1. So here we have 1, 2, 3, 4, 5, and 1, 1, 1, 1, 1. They're all ones. Notice that the x label here is kind of overlapping with the title of the plot underneath it. I can get rid of that by defining the figure as layout equals tight, I think. Let's see if that works. No, that's not right. Um, Actually, I think I have it shown somewhere down below. Mm, well, let's find out if that works. Yeah, that worked. So when I take the figure f and run the function tight layout on it, it spaces it out so that the titles don't overlap with the x-axis and the y-axis. Let's set the x labels and the y labels as well. Oh, let's not. Let's do that later on. So anyway, we have the plot number 0, 0, which plots the y-axis is 1, 1, 1, 1. Let's plot it with some markers as well. I wonder if I can plot it with both circles and arrows. There's the dots, 1, 1, 1, 1. It plot 0, 1 is 1, minus 1, 1, minus 1, 1. So there we have 1, minus 1, 1, minus 1, 1. Let's plot that with O's instead of, with dots instead of lines as well. There we go. Now that plot has dots instead of lines. 1, minus 1, 1, minus 1, 1. Plot 1, 0. That's plotting 1, 2, 3, 4, 5 on the x-axis and 1, 2, 3, 4, 5 on the y-axis. Let me plot that also with dots instead of lines. There it is with dots instead of lines. 1, 2, 3, 4, 5. And then plot 1, 1 is 5, 4, 3, 2, 1. No, it's negative 1, negative 2, negative 3, negative 4, negative 5. So it's going down. So we can create these 4 different subplots, and each one of them is plotting 5 different points, which can be plotted either as dots or as lines, depending on what we would like it to do. So this Matplotlib is an extremely flexible plotting package. As you can see, it has more functions than you'll ever use. One of the functions that it has that's really useful is to be able to plot 2 different things at once. And we'll use this in the homework this week. For example, I can plot the cosine in blue and the sine in orange. And the way I do that is by simply giving the plot function the x-axis for the cosine and then the y-axis for the cosine. And then after that, give it the x-axis for the sine, and then after that, give it the y-axis for the sine. So both the cosine and the sine are plotted at 0, 1, 2, 3, 4, 5, 6, but they have different y-axes. The y-axis is a cosine in blue and a sine in orange. Right? There's a lot. I mean, first of all, we might want to make that much more fine-grained. We can make it much more fine-grained by using the linspace function from NumPy to create a linearly spaced array between 0 and pi inclusive with 100 spaces, 100 steps. And then I can create the cosine and I can create the sine from that. So there's cos will be the cosine and sin will be the sine. Then I'll create a figure, and in this figure I will plot the cosine in blue and the sine in orange. And then I'll do some extra things. I'll set the title. I'll set the title to be the words sine and cosine with 24-point font. And I'll set the X label to read theta in radians, and I'll give it font size 18. I'll set the Y label to read sine of theta and cosine of theta with a font size of 18. And then finally, I'll give it a legend also. I'll tell it, find the first line and label it as the cosine. Find the second line and label it as the sine. And in this case, the first line is blue and the second line is orange. And so it plots it gives me a legend off to the side that shows me that the cosine is blue and the sine is orange. So these are the basic plotting functions in Matplotlib. It does this plots. You've seen that it actually has a lot of other kinds of plotting capabilities, not just plotting. Some of the examples of things it can do a plot, it can do a scatter plot, it can do bar plots, stem plots, fill between plots, stack plots. Let me do just 2 of those. Let me show you how to do a scatter plot and how to do a stem plot. The scatter plot is something that looks like this. It's just a set of dots. And the nice thing about the dots is that you can specify what kind of marker to use and what kind of color to use. So here I'm specifying that the sine should be red dots and the cosine should be blue X's. Matplotlib has a number of different markers that you can use. Oh, here's the markers link. We can bring up the list of all possible markers. You have points or pixels or larger circles or downward pointing triangles or upward pointing triangles or left triangles, right triangles, Y shapes or upside down Y or left Y or right Y, octagons, squares, pentagons, so many different kinds of markers. All of these are possible markers that you can use. There's no reason that you have to use just the circles and the X's. You can use anything you want. There are also a number of different colors. Where does it specify the colors? The colors are not specified here, but the colors include at least red, green, blue, cyan, magenta, yellow, black, and white. Here I'm specifying blue and red. If I want cyan and magenta, let's make this cyan and let's make this magenta. So here I have cyan x's for the cosine and magenta dots for the sine. Let's make these dots, I think it's the capital O that gives me larger circles. Let's see if that works. Nope, that didn't work. What is the marker for the large circle? Small o. That's what I was already using. Oh, I guess the dot is a smaller point. Okay. Anyway, there's the circles for the sine and the x's for the cosine. So that's a scatter plot. A scatter plot is just one where you give it exactly the same points. Notice that I gave it here, theta on the x-axis, cos on the y-axis, then the color and the marker shape. Theta on the x-axis, sine on the y-axis, and the color and the marker shape. So we're using the same plot function for the scatter plot. That's not true for the stem plot. The stem plot looks like this. A stem plot is like a scatter plot, but with lines connecting the x-axis to each point. So you can see how far above the x-axis each point is. And here we have to do each stem plot separately. We type s.stem, give it the x-axis and the y-axis and the color for those markers. So again, if I want to change the colors of the markers to magenta and cyan, I can do that by specifying M and C. Let's do that. Now I have the cosine is in magenta and the sine is in cyan. And you see cosine is this pink color magenta, sine is this bluish green color called cyan. All right, that's everything we need. We have NumPy. We took the cosine of theta and the sine of theta, where theta was linearly spaced. And then we used matplotlib to, first of all, create a figure. Second, create an array of subplots. And third, create a stem plot for each of the different signals in that. Now let's try to do the homework. We're going to do the homework will have three different functions, two of which we'll use all of which I think we'll use matplot, we'll use NumPy. So the first function, 5.1, calculates the center of gravity. Let's look up center of gravity. Let's go to Wikipedia and we'll look up center of gravity. The center of gravity is the point where you balance something. So here this bird has a center of gravity where the finger is. And you can calculate the center of gravity by multiplying by doing this calculation, by taking the mass of every point, multiplying it by the location of that point, and then dividing by the sum of the masses. So that's what we're going to do. We're going to take the location of every point, 0, 1, 2, etc., up to n, and multiply those by the masses, x0, x1, x2, etc., all the way up to xn, and then we'll divide by all of the sum of the x's. So x will be the set of masses, and c will be a scalar, which is the center of gravity. If I run this right now, I'll get 0 because there's nothing in that function. And so I need to edit it so that if, for example, I give it 1, 2, 3, 2, 1, it would calculate that the center of mass is at point number 2. So let's edit that function. We'll go to homework5.py. And let's see, we want to take x and take its dot product with the NumPy array that goes from 0 up to the length of x. So let's say that r is equal to NumPy a range from 0 to the length of x. And now c will be the dot product between r and x divided by the sum of x. That should give us the dot product is in the numerator and the sum of x is in the numerator. So that should give us everything we need. Let's save that Python file. And let's go back to our Jupyter notebook. We will reload homework 5, and then we'll calculate the center of mass of the array 1, 2, 3, 2, 1. And so the center of mass is at point 2. If I make this second element a bit bigger. Let me make this second element a little bit larger so that this is tilted to the left. Now the center of mass will be a little bit smaller because I've tilted this array a little bit to the left. Now the center of mass is just 1.9. If I balance it out again by adding some more mass on the right-hand side, now the center of mass will shift to the right again. And I've got a center of mass of 2.0 again. So that's just this calculation. It's finding the center of mass of the bird. All right, problem 5.2 is a matched identity. This is just taking an array X and creating an identity matrix which is the same size as X. It doesn't matter what the content of X is. If X is 1, 2, 3, 2, 1, that has 5 elements. And so the resulting NumPy array should be a 5 by 5 array containing all ones except for the diagonal. And we should be able to do that in just one line. That's just going to be the identity matrix with an argument, which is the length of the input matrix, the input vector X. Let's save that and let's go back and test it. If I run that, import it again, and there's the identity matrix, which has a length of 5. If I add 3 more elements here, I've just increased the length of X to a length of 8. The contents of X don't matter. It just creates a larger identity matrix, an identity matrix of size 8 by 8 instead of 5 by 5. And then finally, I'm not going to actually do any plotting inside of the homework, but we are going to calculate a sine and a cosine. If I give you a starting time and an ending time and a number of steps, then you should create a t array, which is linearly spaced between t start through t end inclusive, with a number of steps equal to t steps. So let's go back to homework 5. That means we're going to create a linearly spaced array, np.linspace, between t start and t end, with t steps in between. All right, let's save that. And if I then the next thing I want to do is to take its cosine, and the next thing I want to do is to take its sine. So if I create, for example, the a linear array between 0 and pi with a length of 20, well, now it's an error, but I need to take the cosine and the sine. Let's say x is equal to the cosine of t and y is equal to the sine of t. And if I go back here, I will create a linear array between 0 and pi with 20 steps, and then I'll calculate the cosine of that plot in a Matplotlib window. And there's the Matplotlib window with the cosine in red and the sine in blue. You can check to make sure that your homework matches what the grading is looking for by running import lib reload grade, and you can see that it claims that I got 100%. So as soon as you get 100%, you can go to GitHub Desktop and check it back into your GitHub repository. It looks like it's showing all the work that I just did. So let's check it in. We'll commit it first of all, and then we'll push it to the origin. And then let's go to my GitHub account and see if we can check to make sure that it's really there. In my student account, in lecture 5, in homework 5, I now have the center of gravity, the matched identity, and the sine and cosine. So if I copy this URL, then I can go to the course web page, Canvas. Just pulling up Canvas here. Here's the course web page. And here we go. Enter the URL for your copy of homework5.py. So if you enter your URL here, I should be able to grade your homework and give you the points for that assignment. That's all for today except for attendance. So let me go ahead and run the web attendance registration. Let me go ahead and stop the video at this point.